In the third section of our first lecture on Vision Deep Learning, we'll begin by exploring some crucial AI development tools before we delve deeper into the core concepts and engage in hands-on activities. Understanding these tools will provide a solid foundation for the practical work we'll do later in the course. We'll cover TensorFlow and PyTorch, two of the most widely used frameworks in the field of artificial intelligence. Let's examine the general AI developing process, or pipeline. It's important to understand that while the core principles remain similar, the specific steps in the pipeline can vary significantly depending on the type of machine learning being implemented, whether it's standard machine learning, deep learning, or a specialized branch such as Vision Deep Learning. Today we'll explore one such example of a pipeline specifically designed for developing AI applications using the Python programming language. For me, I would divide it into 5 steps. This example is not the only way to structure your AI development process, but it serves as a practical framework that can be adapted or expanded based on the specific requirements of your project. First is data collection. This is the foundation of any AI project. We need a robust data set along with the correct answer key, which involves dataset processing and EDA. Then, once we have our data, the next step is pre-processing. This includes cleaning the data, creating training and validation splits, and applying data augmentation techniques to enhance model robustness and prevent overfitting. Then, we have model building. At this stage, we survey various neural network architectures or consider developing a custom model. Network Architecture Search, NAS, can be used here to automatically select the best architecture based on the data and the task. Then, we train a model, and once the model is trained, we analyze its performance using various statistical methods and visualizations. Then, if the model performs well on the test set, then it might be ready for the next stage, which is deployment. As we explore the AI development pipeline, it's important to recognize that different roles and responsibilities emerge depending on which part of the pipeline an individual is involved in. These roles often require distinct skills and contribute in various ways to the development and deployment of AI systems. First is UI/UX designers for AI systems. Their work is crucial in applications where models' outputs are directly interactive with end users. Second is data scientists or AI researchers. These professionals are typically more involved during the initial stages of the pipeline, such as in data collection, pre-processing, and result analysis. Next is developers and engineers. If the results are not satisfactory after going through a pipeline once, the iterative nature of the AI development process requires us to cycle back to earlier stages. We may need to revisit data collection to enhance the dataset or improve our labeling accuracy, especially if there were errors or inconsistencies in the initial labels. It's essential that only experts in the relevant medical field handle the labeling to ensure accuracy. If the model fails to meet performance expectations during the training stage, it's crucial to revisit earlier stages of the AI development pipeline. We might need to reevaluate the architecture of the neural network or adjust the hyperparameters used during training. For example, in tasks involving natural language processing, where the subtleties of language can greatly affect output, fine-tuning the model with different layers or activation functions might be necessary. Additionally, expanding the training dataset with more varied examples or increasing the number of epochs during which the model trains can also be crucial steps to improve accuracy. Now, let's explore a little more on EDA. Exploratory data analysis, or EDA, is a foundational step in the AI development pipeline, essential for gaining insights into the dataset before diving into more complex modeling. EDA involves a series of techniques aimed at understanding the distributions of data, detecting outliers, visualizing relationships between variables, and identifying patterns or anomalies that could affect the performance of machine learning models. By using statistical summaries and graphical representation, Data scientists can ensure the data is clean and appropriately prepared for the modeling stage. EDA also helps in verifying the quality of data collection and labeling, which is crucial in tasks requiring high accuracy, such as medical diagnosis or financial forecasting. Through this process, potential issues can be addressed early on, which helps in designing more effective and reliable AI systems. By understanding the dataset, teams can make informed decisions throughout the pipeline. Next is data processing. This is basically a step where we refine the data so that AI can learn better. As we discussed in the previous session, the surge in machine learning and deep learning wasn't just due to having more data, but rather because we had access to a lot of refined data. Data processing involves further refining this data. For example, a stream of images for a video might be formatted to ensure uniformity in size, resolution, or format across the dataset. This uniformity is vital because consistent data input helps improve the model's learning efficiency, reducing potential biases or errors that could arise from irregular data formats. A lot of techniques go into data processing, but the one we'll discuss further is fold splitting, as we'll explore in our third lesson on data processing. Fold splitting is crucial for creating distinct training, validation, and test sets. This division is crucial for training models robustly, allowing us to fine-tune the algorithms on the validation set and finally evaluate their performance on the test sets. Moreover, by systematically separating the data in this way, we ensure that our model is not only optimized for the accuracy unknown data, generalizes well to new unseen data. Moreover, in scenarios where the available data might not be sufficient to train our models effectively, we employ a technique known as data augmentation. This involves making slight modifications to the existing data, such as rotating images, changing scales, or altering lighting, to artificially increase the size and diversity of our dataset, which helps in enhancing the model's ability to generalize well. After the data is processed, we move on to building models. This stage involves conducting a neural network survey to select the appropriate architectures, building the neural network, utilizing techniques like neural architecture search. NAS automates part of the model building process, helping to identify the most efficient architecture tailored to our specific data and task requirements. Then we move on to the training phase. This step is crucial as it involves the optimization of the neural network. Neural networks, as we'll learn later, have numerous parameters that need fine-tuning to achieve the best results. This optimization process adjusts weights and biases based on the data and the specific task, aiming to minimize errors and improve accuracy. During this phase, we can also explore advanced techniques such as ensemble learning. Additionally, transfer learning can be employed when we have a pre-trained model on one dataset and we want to adapt it to a new but related dataset. If the analysis indicates that the model performs well, we can proceed to the development phase. This step involves integrating the AI system into a real-world environment where it can start delivering practical value. Unless the model meets the expected standards of performance, the AI development process requires us to revisit and review each stage meticulously. So we have to go back to the beginning and think, was it lack of data, or was it bad labeling, or was it not as good of an EDA we did, or was it inadequate pre-processing, or do we need more augmentation, or was our augmentation pattern too simple, or were we using the newest model available, and if not, am I able to come up with a new model, a new custom model? Then we would have to go to the model training process as well and check whether we need to further fine-tune the parameters for the models. Then, after creating a lot of these new models, we might make an ensemble of these to try to make a better model. Or, if the model struggles with limited data, we could apply transfer learning techniques to leverage insights from similar tasks. This approach allows you to utilize a pre-trained model that has already learned substantial features on a large dataset, thereby significantly reducing the need for a bigger dataset. Then we analyze our results once again. We not only check the performance, but also take a look at the statistical values to better understand the model behavior. This analysis can reveal subtle dependencies and interactions within the data that are not immediately apparent. Then, we visualize the data once again. We utilize visual tools to dissect the model's decisions, looking for patterns and errors or successes that can guide further refinements. The advantage of working with vision data is that we can do easy visualization for the data. And that is because vision data allows for straightforward and intuitive visualizations. In the realm of evaluating machine learning models, we often discuss terms like intrinsic versus extrinsic evaluation. Intrinsic evaluation involves examining the dataset as a whole to understand the underlying structure and distribution of the data. This holistic view can reveal patterns or anomalies that are not apparent when looking at individual samples. On the other hand, extrinsic evaluation focuses on how well the model performs on individual tasks or instances. And this iterative cycle is what a data scientist does.